Yes. Now it is recording, I think. Yes. So I was asked to deliver 3 units. The first one is the open channel flow, and the second one is sediment transport, and the third one is the groundwater flow. So today I will start with this open channel flow part. As Dr. Chandana mentioned, whenever you feel that you don't understand anything, please do not hesitate to stop me so that I can explain it again. In the beginning, I will go very slowly you to understand the concepts. Then hopefully once you understand the basic of this open channel flow, you will be able to work in your own. So I read the booklet that has provided to you by the Open University, and it is a very detailed one with many examples. And also in myself itself, I have provided you an assignment so that when you do this assignment and do the examples that you have in your booklet, you should be able to cover almost all the content of this open channel flow. All right. So since we have very limited time, I will quickly jump to the content for today. All right. So let me go to the presentation mode. Right. I hope you can see it. Students, could you please comment? Students, yes. I need your feedback. Can you see it? Yes. Yes. Yes, I always like if you can speak. Okay. Right. Thank you. Now, the expected course learning outcome of this unit is to explain the standard approaches and the formulas to solve and design open channel flow. So basically, we will be discussing some familiar equations to you, like the energy equation, momentum equation that you learn in fluid mechanics. And also we will discuss the Manin equation. Probably the Manin equation also you have already studied under the hydraulics section, but if not, I will discuss it in detail today. So the content I am expecting to cover is the open channel flow characteristics, then the application of energy equation, right? So we cannot talk about the open channel flow or the pipe flow without the energy equation. Then the force momentum equation, in other words, that is the Newton's second law. Then we will talk about the uniform flow in open channel and then the non-uniform flow. So I have 2 hours today, so I hope to cover almost all of them. But in the beginning, I will go slowly, but even if I was not able to cover all 5 topics, you should be able to do the self-study once you get the basics. Okay, so that is my idea. Right. So can someone tell me what is the difference between the pipe flow and the open channel flow? Did you study the pipe flow? Students, have you studied the pipe flow?
The open channel has exposed to the atmosphere.
Yes, very good. Open channel is always open to the atmosphere, right? So what is the difference of that to the pipe flow? In both open channel flow and pipe flow, we talk about 3 different head terms, right? So the elevation head, then the pressure head, and the velocity head, right? So these are the basic 3 head terms. So you probably remember discussing about the EGL. EGL means the accumulation of the elevation head, pressure head, and the velocity head. In pipe flow, if you have a constant diameter pipe, always this EGL and HGL parallel to each other. That is what you learn. So the EGL is the total head and the HGL is the pressure head plus the elevation head. So the difference between these two we define as the velocity head, right? So that when the water go from higher head to the lower head, always it is in the expense of the pressure and the elevation. So the pressure and the elevation change but the velocity remain constant if the pipe diameter is the same. But come to the open channel flow. Now you understand that on the surface, the pressure is always atmospheric pressure, right? Therefore, what will happen, this water level will change. Level will change. Inside the pipe, the water level is always constant. Why it is? We are talking about a pressurized flow, right? But here, what happened, the water level will change and correspondingly, the velocity will change, right? So that is the main difference between the pipe flow and the open channel flow. Right. So we will be discussing several equations like the Manin equation, and also we will discuss the Froude number. When we discuss these terminologies and the equations, there are certain parameters that we need to know. So I will discuss these parameters in detail first. So having that understanding, it will be easier you to study the governing equations. All right. So what is the most basic equation that you learn in pipe flow or in open channel flow? Whenever the flow rate is included, what is the most basic equation? Anyone? The most basic equation is Q is equal to AV, right? So can someone tell me what are these parameters? Q is of course the flow rate. A is the cross section area, and velocity is the what? What is this V? What velocity it is? It must be the average velocity. And there is one condition here. The area, the cross-section area that you consider should be perpendicular to the average velocity. That is the condition. That now you understand that whenever we are going to find out this flow rate, it doesn't matter whether we are talking about the pipe flow or the open channel flow, we always have to have the idea about the cross-section area, right? So the cross-section area for different cross-sections are like this. So these are the most common cross-sections that we use in the field, right? It can be a rectangular channel, or the trapezoidal channel, triangle, or a circular channel, right? Circular channel, in fact, is more like the pipe flow. But what is the difference here? The pipe flow is a pressurized flow, so that the entire cross-section contribute for the water flow. But let's say the stormwater distribution system, there when we use a circular cross-section, it is not necessary that this water flow always to be pressurized. It can be an open channel flow. So what happened in that time? You see, this part of the channel is filled with air. In other words, it is open to the air. That is why we call it is the open channel flow. All right. But you understand, on all these cases, the free surface is open to the atmosphere. Now, we need to understand what are these parameters that we will use in the equations. Like, for example, the area. It is very simple to understand. If you use a rectangular cross section, area is simply B multiplied by the water level height, right? Now, do you think that you can manage this area for the trapezoidal section? I will quickly show only for the trapezoidal section, and I am expecting you to work your own for the triangular section and the circular section. All right. So very quickly, I will show you this one. Right. Suppose that we have this kind of a trapezoidal section. Now the slope here is m to 1. And this width here is b. Suppose that we have the water height, this is y. All right. So we want to understand what is this cross-section area contribute for the water flow. Right. So how do you do it? If you say this is capital T, capital T. And let's say this height here is y, so that this length here is a. Then can you write a in terms of m and y? I'm sure you can, right? So I will quickly show you. This is a divided by m should be equal to a divided by m should be equal to y divided by 1, right? So a is equal to my. Now use the trapezoidal equation, sorry, the equation you to find out this length here. Let me say this is c. So what is this c here? C is equal to a squared plus y squared and square root of that. So that a is equal to my. So when you take the a squared, you can take the y squared out. So that it become y. This is equal to m squared plus 1. So I expect you to know how to get this kind of a simple equation. All right. So now we have all the parameters we need to find out the area. So what is area now? A is equal to what? This T. How do you write T? It is equal to B plus 2 times of A. Here A, this is also A if the slope is constant, right? So B plus 2 times of A plus again B plus B divide by 2, then the entire thing you can multiply it by the height. Multiply it by the height, right? So substitute these parameters, then you should be able to get this equation here. All right, this one. This is the equation for the area. I expect you to try for this one and this one. Okay, now area is a simple concept. What is the wetted perimeter? Wetted perimeter is simply the length of this section wetted by water. Again, it is a simple concept. If you take this kind of rectangular section, now you see this is the water level, right? So that what is the length wetted by water? It is this length, this one, only this. So what it is? That is b plus 2 times of y, right? B plus 2 times of y. So I need you to try how to get it for the trapezoidal section. Now you understand. For the trapezoidal section, this is the wetted perimeter, right? This is the wetted perimeter. Then there is a very important parameter that is called the hydraulic radius. Probably you learn it in fluid mechanics and the pipe flow. Hydraulic radius, what is the definition? Can someone tell me? Anyone? What is the definition of the hydraulic radius? Okay, let me explain. Hydraulic radius is area, this hydraulic radius, all right? Area divided by the wetted perimeter. Area divided by the wetted perimeter. That is the definition. Okay, so in this case, our area is by for the rectangular section. Wetted perimeter is b plus 2y, right? So this is a very common parameter that we use in governing equation like the Manin equation. So we will discuss them today. Area divided by the wetted perimeter. Then top width. Top width. So here top width, it is equal to b. If it is a rectangular section, this top width, in other words, that is the width of the water surface, that is equal to b. But here that is not very easy. You will have to calculate it in terms of b and m. I'm sure you can do it, right? So this is the top width for the trapezoidal section, right? So I'm expecting you to able to derive this, right? Now the top width also kind of common. So we will discuss it today in detail. And hydraulic depth, again, the definition is that the hydraulic depth, that is D, D is equal to the area, right? Area divided by the top width that we have here. For example, if it is a rectangular section like this, area is equal to by, the top width is equal to b, so that b to b cancel, it is equal to y. It is equal to y, right? Now think about the trapezoidal section like this. So the hydraulic depth, do not misunderstand this hydraulic depth. For the rectangular section, yes, it is equal to the water depth. It is equal to the water depth. That is why we got y. But hydraulic depth has a different definition. What is that definition? That is equal to the area divided by the top width. So now for the trapezoidal section, the area is this one. So we have it in here. Divide by what is the top width? B plus 2 times my. So we have it in here. All right. So these are the definitions that we are going to use when we talk about the governing equations, like the Manin equation, then the energy equation. So we are going to need them. All right. So I hope it is clear. Do you have any questions? No questions. Okay. So let's move on then. Right. Now the open channel flow, we will discuss them in different categories. For example, the steady and the unsteady flow. Can someone tell me what is a steady flow? Yes, anyone? What is a steady flow? You can speak or you can put the message on the chat box.
The depth of the flow will constant. No?
The depth of the flow is constant. That is for the uniform flow. Now the steady mean if the flow characteristics does not change with the time. For example, take the velocity. If the velocity does not change with the time, that is called a steady flow. Unsteady means it changes with the time. Right? I hope it is clear. The uniform flow means the flow characteristics does not change from point to point. Right? So in that case, it is called a uniform flow. Now think about if you have a water flow with a constant velocity, in that case, the water depth will be constant, right? So the case like this, the flow in a channel is said to be uniform if the flow depth, and therefore the average velocity remain constant, right? So the flow is said to be non-uniform or varied, indicating that the flow depth varies with the distance in the flow direction. That is along the longitudinal direction, longitudinal direction. So we are talking about the average velocity, and if it remain constant along the longitudinal direction of the channel, then we say that it is a uniform flow, right? So this is the longitudinal direction. Suppose that this average water velocity when you consider a cross section somewhere here, if it is the same when you go to the downstream, then that is called a uniform flow. But think about this. When you take the cross section, that is entirely a different story. The cross section like this. Why it is? Near to the channel bed and near to this wall, because of the friction, the velocity is practically zero. Velocity is practically zero. So probably you remember when you draw the velocity profile towards the water surface, we draw it like this. Velocity increases as we go towards the water surface. This is how the velocity change, right? So velocity closer to the bed is practically zero, right? So when you take a cross section, that is how the velocity change. That is why we discuss here about the average velocity, right? Average velocity for that particular cross section, average velocity, right? So I hope you understand that. Then that is about the uniform flow. Non-uniform flow, again, we talk about the rapidly varying flow and the gradually varying flow. So today we will discuss for hydraulic jump. That is where the water velocity rapidly change and the flow become turbulent. So energy losses. So we will talk about these when we talk about the non-uniform flow. Right. Now, when it comes to the pipe flow, again, you remember we discussed about the lamina and the turbulent flow. So the parameter we use to define the lamina and the turbulent flow is called the Reynolds number. If it is the pipe flow, what is the threshold we use? Anyone? What is the threshold we use? It depends on the application. For the pipe flow, we use the threshold 2000. Whenever the Reynolds number is less than 2000, we call it is the laminar flow. If it is more than that, the flow is becoming turbulent. There is a transition region, of course, but flow is becoming turbulent. But it depends on the application, whether you are applying it for the pipe flow, open channel flow, or the groundwater flow. For example, the groundwater flow, to apply the Darcy equation, we need the Reynolds number to be less than 1. So the threshold there is 1. But when it comes to the open channel flow, we call it is a laminar flow if the Reynolds number is less than or equal to 500. It is not 2000 now, it is 5,000. Sorry, 500. But if it is more than 2500, then it becomes the turbulent. In between, there is a transition region. Right? So that is how we define the laminar and the turbulent flow. Right. Now, as I said, when the flow rate is changing, right? Also, when the flow become non-uniform, then the flow may change gradually, or it can change rapidly, right? Or it may become a uniform flow. So we should be able to understand how this water depth change according to this flow characteristic, right? That is the most important thing. The point is that you need to understand what is the cross-section of your channel that you are going to design. And when you design the cross-section, if this height cannot properly account this kind of a variation, then what will happen? The water will start overflowing, right? So this is what normally happens. So you should be able to understand what is the water level variation in different status. If it is a gradually varied flow, how the water level change. When the flow become rapidly varying, or we call it is the hydraulic jump, then how the water depth change. When the flow become uniform, then again, what is the water depth, right? So that these are the points, or these are the different status that we are going to simulate by using different equations. Okay. Right. So we will start with the uniform flow in open channel, right? So the first equation that we use is the momentum equation, and we will use the energy balance. Do you remember how we define or derive this momentum equation? What is the basic equation we use? That is called the Reynolds transport theorem, right? In Reynolds transport theorem, when we use the momentum as the extensive property and the velocity as the intensive property, we derive the momentum equation, right? So suppose that accumulative term of the momentum inside this control volume that we consider is 0, then we can write the net force or time rate of change in the momentum, right? Then it is equal to net force. right? Net force is equal to time rate of change in the momentum there. So we are assuming that the accumulation of the momentum inside this control volume, water volume, is equal to 0, right? So since we are talking about a uniform flow, we can say that the net force is equal to 0. Net force is equal to 0. There is no acceleration there, right? So that the net force is equal to 0. So what are the forces acting on this water body? Now here we have this channel bed, right? So this is the water surface, this one here, water surface. So this is the control volume that we are selecting now. In this control volume, we are going to analyze the force balance, right? So what are the forces? We have the F1 and F2. These are the pressure terms coming from the both side, the pressure term. In addition to that, there is something called the shear force or the friction force. Where is it? If you consider this kind of a trapezoidal section, that is why we discussed the parameter weighted perimeter, right? So where do you have this friction force? Friction force is along this weighted perimeter. This is where you have the friction force, right? So if you consider the shear stress is tau naught, shear stress is tau naught, how do you find out the friction force or the shear force? You know that shear stress multiplied by the area, shear stress multiplied by the area is equal to the shear force. So what is this area now? That should be, let me draw this channel like this. This is the longitudinal direction, right? So that in that case, this weighted perimeter multiplied by the length will be the shear area, right? So that is why we write P. P is the weighted perimeter multiplied by the length. Length is the length of the channel. Now the tau naught is the shear stress. So the shear stress multiplied by the area will give you the shear force, right? Now that is the one force acting on this water volume. The next one is the gravitational force, right? So what is this gamma? I'm sure you know it. What is gamma? Gamma stands for anyone? What is gamma? Vanushan, can you tell me what is gamma that you studied in pipe flow or the fluid mechanics? Lakmali, what is gamma? Lakmali, you can hear me, right? Okay, we have not the fluid density, no. Gamma is equal to, or gamma is defined as the specific weight. Very good. That is the specific weight. That is equal to, gamma is equal to the fluid density, that is rho multiplied by the acceleration of gravity. If you consider the water, that is equal to 9,810 Newton per meter cube, right? So you consider what is that gamma. Gamma, that is the specific weight, multiplied by the water volume, that is cross-section area multiplied by the length, will give you the weight, right? Then we consider what is the component of that weight along this direction, So when the water flow into from the upstream area to the downstream area in this direction, the weight component also is acting into that direction. But since the water is flowing from the upstream to the downstream, the shear force is acting in the opposite direction. That is why it is negative here. So these are the two forces. But why we did not consider this F1 and F2? They are the pressure forces, and we are talking about the uniform flow, so that this depth is constant, water depth is constant. That is why the F1 is equal to F2, right? So that now from this equation, from this one, we can write it like this, a very simple equation. So the shear stress is equal to gamma multiplied by R. What is this R now? Is the hydraulic radius. Hydraulic radius. And the sine theta, right? Sine theta of the coming for this weight component, we are talking about the open channel flow. Normally, the gradient or the slope of this open channel is very, very small. We are talking about a very small gradient. And in mathematics, you know that if this theta is normally less than 10 degree, you can say the sine theta is approximately equal to the tan theta. Now it is approximately equal to the slope of this channel, or the slope of the channel bed, that is S0, right? And for the uniform flow, the slope of the channel bed, it is equal to the slope of the water surface. Why it is? This channel slope is equal to the slope of the water surface. Why it is? It is because this is a uniform flow, so that the water depth is constant, right? That is why it is equal to the water surface. And it says that it also equal to the SE. What is this SE? That is the slope of the EGL. Slope of the EGL. Why it is constant? Or why it is same? The reason is that, again, we are talking about a uniform flow. If the flow is uniform, the velocity head is constant, right? V squared over 2G, that is the velocity head. So this velocity head is constant if you are talking about a uniform flow. That is why when the flow is uniform, the river bed or the channel bed is slope of the channel bed is equal to the slope of the water surface. It is equal to the slope of the EGL, right? That is the characteristics of the uniform flow. All right, so now we have this equation. Now, in like 1769, right? So in 18th century, Anthony Chisi, he's the one who first studied about it, right? So he found out that this shear stress, tau naught, we can write it as a function of the average velocity. So he wrote it as kV squared, right? So this k is a constant and v is the average velocity. Now we can write this equation, this one, right? This one, right? So after that, what he did, this one, this equation, now he made it equal to this one here, right? So the same equation, and he wrote the velocity, average velocity is equal to the area divided by the wetted perimeter. When you simplify this equation, this is what you get. Area divided by the wetted perimeter. In other words, that is equal to the hydraulic radius. And S0 is the slope of the channel bed. And we have two parameters here. That is gamma and K. Gamma and K, they are constant. So he defined it as C, right? So this equation now simplified to a simple form like this. So this is the Chisi equation. But unfortunately, he was unable to use it because this C was not easy to find it out, right? So later on, Manning, he did some further research And he found that this TC coefficient can be written like this as a parameter of, again, the hydraulic radius. And there is another parameter here called the Manning coefficient. Right. So now we substitute this C into this equation and we get an equation for the average velocity. Average velocity. Right. So this is called the Manning equation. In fact, it is known as the Cheesy-Manning equation. The reason is that Cheesy is the one who developed it first. Then Manning further developed it in a way that it can be used for the practical application. Right. So now this V we can write in terms of the hydraulic radius and S naught. In the original equation, we have the S naught. But if you are talking about the uniform flow, we know that the channel bed, the slope of the channel bed is equal to the slope of the EGL line, right? So that we can write it like this, SE, that is the slope of the EGL line. Now this is the average velocity. Again, we know that Q is equal to AV. What we need to understand is in a channel, what is the flow rate, not the velocity. So we can write this Q in terms of the area and the velocity. So this is the final equation that we use, right? So here area is the cross-section area of the channel. This is the hydraulic radius. Hydraulic radius is equal to area divided by the wetted perimeter. And SE is the slope of the EGL line, right? So these are the parameters we need to find out the flow rate. But remember, whenever you are applying this Manning equation, keep it in mind that it was developed for the uniform flow condition. Uniform flow condition, right? So that is the main assumption that we use. Then this one here is for the, if you are using the SI unit. Again, keep it in mind that this is for the SI unit. But if you are using the US unit system, instead of 1, you have to use 1.49, right? So this is the equation if you are using the US unit system. Now, it is a matter of finding this N to find out the flow rate, right? So we have to find out what is Manning coefficient. So the Manning has defined different coefficients for the different type of channels. For example, you will do open channel flow experiment, right? There, it is a glass channel that we have. In that case, it is a very smooth surface. Therefore, the Manning coefficient is quite small, like 0.01. But if you are talking about like natural channel, then you can see the Manning coefficient change, right? So the roughness become higher. So the magnitude of this Manning coefficient indicate the roughness of the surface. Roughness of the surface. Is it clear? So far, do you have any questions? Students, do you have any questions? Do you need any clarification? Okay. So no questions mean you understand it. So that is how I understand it. Okay. Right. Now, the application of this Manning equation. Right. So you see what we interest to find out. In a hydraulic design, basically what we need to understand is what should be the cross-section area. Why it is? Cross-section area depend on, or the cross-section area affect for the excavation that you have to do. Then if you are going to use concrete, then what is the amount of the concrete that you have to use for this channel, right? So all these decision has to be made based on this cross-section area that you design, right? So now for a given flow rate Q, then there are several parameters that we need to find out. What are they? We need area and the velocity. Velocity is, average velocity is in terms of hydraulic radius and the slope of the EGL. Now you see we have the area here. So again, the area comes for the hydraulic radius. So this is not going to be a linear equation. This is a non-linear equation. So nowadays you have these sophisticated calculators and the computers so that the iteration can be done very easily. But in earlier times, they didn't have this kind of facilities. So what they did, probably you remember the Moody diagram. Moody diagram is you to find out the friction factor based on the Reynolds number and the relative roughness. So the Moody developed that diagram, knowing how complicated the Colebrook equation is, right? So similarly, you to find out the dimension of this channel for a given flow rate and given other site conditions, this kind of charts have been developed, right? So this is for the trapezoidal and rectangular section. This line is for the rectangular section. Other 4 lines here are for the trapezoidal sections. So what are the parameters we have? We have M here. That is the slope of this channel. This one, the side slope, right? So what are the other parameters we need? We need to decide what is the width of this channel we are going to use. Depend on the width, this Y will change, the water depth. If you are using a smaller width, then you will have to use a larger hydraulic depth, right? So what we do, we find out or we decide what is the B first. It will depend on your site condition, right? Maybe the width is restricted. In that case, you will have to change the Y to accommodate that flow rate, right? So what we do, we have an understanding about the flow rate, right? I'm sure you have taken the hydrology course, right? So how do we find out this flow rate? We have this kind of a catchment area. Suppose that this is where you are going to design that hydraulic structure, so that this is the flow rate that is coming from the catchment area, right? What is the direct runoff? What is the base flow? So you add them together to find out this design flow rate. Probably you remember learning about an equation like the rational equation that is equal to CIA. Peak flow is equal to CIA, right? So you find out what is this peak flow. That is the one that we bring here, peak flow, right? So now for that, what is the Y that we need to carry that flow rate for a given channel width? K is depend on the unit. It can be 1 or 1.49, depend on the unit system that you use. Then the S naught is equal to the slope of the channel bed, longitudinal slope. And B is the width. By knowing them, then simply you can find out what should be this ratio, Y over B. Again, you have B so that you can find out Y. That is the advantage of this kind of a type curve. Simply by knowing the design conditions like the flow rate and the site condition like the slope of the channel and the width, you can find out what should be the Y. All right. So remember that is for the uniform flow condition, uniform flow. All right. Yeah, we also can solve the Manin equation. Nowadays, you have these sophisticated calculators, computers. You can solve the Manin equations very easily. Right. So earlier, type curve was for the rectangular and the trapezoidal sections, and this one for the circular section. Right. Again, the same parameters, similar parameters you have in here. So by knowing them, you can find out what should be this. All right. So this D naught here is this height here. What is it? That is the diameter of the pipe, right? Diameter of the pipe. By knowing it, you can find out what is this normal water depth. Right. Hope it is clear. Right. Now you understand the basic. right? So we need to find out what is the cross section of the hydraulic design that we are going to use. Right. Now, in any hydraulic design, there are several aspects we need to consider. I will discuss only two of them. These are the most important criteria. What are they? They are the technical criteria and the cost, economical criteria, economical constraints, and the technical criteria. So let me explain it like this. I'm sure you have learned it in a hydrology course, all right? But I will discuss it again very quickly because you need to understand these basics, why you are doing this kind of a design, right? So suppose that this is your catchment area, all right? So when you have rainfall, you have the river flow here. So you are going to design a culvert or an open channel to carry this water, right? So that is the basic idea. Now, when you are designing it, you use the concept of the return period. Suppose that, have you studied this rational equation? I need you to answer yes or no. Have you studied the rational equation?
Yes.
Yes, very good. You have learned it, right? So there, the peak flow is equal to CIA. How do you find out this I? I is the rainfall intensity, right? You use the curves called the IDF curves. Intensity, duration, frequency curves. Frequency. Let's say this is 10-year, 25-year, 50-year return periods, right? Now, depend on the return period that you use, this rainfall intensity is going to be different. The higher the return period, higher the rainfall intensity, right? So why this is even important, or how it relate with the risk, hydraulic risk? You remember the exceedance probability, P, X is larger than or equal to a particular threshold. This is equal to 1 over return period. That is how we calculated the risk, hydraulic risk, or the risk of failure in a hydraulic design. So the exceedance probability of a rainfall event, that is equal to 1 over return period. So now if you are using a smaller return period, then the exceedance probability is, let's say you are using 10-year return period, exceedance probability is equal to 0.1. But if you are using 100-year return period, the larger one, then it becomes 0.01. Now the exceedance probability is smaller. So that if you use this rainfall intensity in your design, now you are safer than using a smaller return period. So you understand that concept, right? So if you are using larger return period, then you are talking about the larger rainfall intensity. So that larger rainfall intensity mean larger peak flow. Larger peak flow mean your cross section, your channel can handle a larger flow rate. So that if you plot the relationship between the risk, as you see here, right? This is the design return period. Design return period, that is T. And then the damage that it happened, damage. If you use a smaller return period in your design, then the damage somewhere here can be very significant. Why it is? A smaller return period mean you are talking about a smaller peak flow. So that now you are talking about a smaller cross section. Cross section is smaller. So if you have a very large or very intense rainfall event in the upstream, probably this cross section now will not be able to handle this water flow. So what happened? The area start flooding, right? So that the damage can be very high. But if you are increasing the return period, you are talking about larger rainfall intensity, larger peak flow. so that now you need a larger cross section like this, so that the damage is now becoming smaller. Right? So it is always better if you can use a larger return period in your design. But what is the drawback? Larger return period mean larger cross section. Larger cross section mean you have to spend more money for the construction, for the excavation. You have to spend more money, right? So as the return period increases, the cost increases. Therefore, you need to have a balance between these two. Optimum solution is like this. You need to have a balance between the damage and the cost. That is why don't blame the engineers always when there is a flood. If the engineers have done the design correctly, they have done it for this optimum condition. That is the balance between the expected damage and the cost. Therefore, whenever you have an event with higher return period, it will not be able to carry this, or the channel will not be able to handle this larger flow rate. But there will be a damage, right? There will be a damage, but if you consider the initial cost, you have to expect that kind of a damage. That is why in a design, you have to consider these constraints. You have to consider the economical side of that design. You have to consider the technical side. In addition to that, there are many other criteria like the ecological, environmental, right? So all these constraints must be decided, must be considered, right? So that is called a hydraulic or the hydraulics design, right? Engineering, economic in water resource planning, right? Now, why did I discuss this? Now, when you are going to design a hydraulic structure like an open channel, then we need to understand what is the optimum way of designing it. Now take a trapezoidal cross section like this. Can we design it in a way that it must carry the flow rate what we need? Flow rate what we need, Q is constant. No matter what, this flow rate must be delivered from this cross section. So if the Q is constant, the area also constant. But can we design this hydraulic section in a way that it minimizes our excavation cost, it will minimize our construction cost while satisfying this Q and A? That is the meaning of this kind of a design. All right, so I will quickly go through this one. I hope you understand the basic, right? So that now I will go quickly through the derivation of this equation or derivation of this cross section. So what should be the dimension that it satisfy the technical criteria, or in other words, we call the hydraulic efficiency. It satisfies the hydraulic efficiency and while minimizing the construction cost. So if you need to minimize the construction cost, what you should do? Any idea? If you need to minimize the construction cost of this section, what you should minimize?
The angle and slope, no?
Yes, exactly. Actually, you need to minimize this wetted perimeter. Suppose that you are going to construct a concrete channel. Then the amount of the concrete will depend on this wetted perimeter. It is that simple. And also the amount of the excavation will depend on this one, wetted perimeter. So you are going to minimize this wetted perimeter while keeping the A and Q constant. Okay, so I will explain the basic idea. So I need you to practice this derivation. All right, very important one. I need you to practice how to get it. Right. So the basically for the trapezoidal section, area is this one in terms of the width and the slope and the y, right? Y is the variable now. Now, we need to minimize the slope, not the minimize, actually optimize. Optimize it in a way that it will minimize our wetted perimeter while carrying this flow rate. So I will consider this is A, that is the cross-section area, and this is the wetted perimeter. So these are the two equations that we derived earlier for the trapezoidal section. Now you can understand that they are in terms of the width, y, and the slope. So what we do now, we know that we have the b, that is variable, m also a variable. So what I will do, I will use this a in the equation. What I know is a should be constant. A should be constant. So I will use a as a parameter to reduce the number of variables in my equation. So now I can write this wetted perimeter without b. Instead of b, I use the parameter a. Now it reduced to the two variables, y and m. A is a constant. Right. This is the wetted perimeter. Now what I do? I need to minimize it. So what I do, or how do I mathematically minimize it? I take the first derivative, dp over dy. Right? So suppose that if you plot a relationship between this y and p, and if you take dp over dy, when it is minimum, dp over dy is equal to 0, right? That is the concept we use. So you take the first derivative of this one with respect to y. With respect to y, dp over dy first, and you get this equation. If it is minimum, we need to make the wetted perimeter minimum. We make it equal to 0, right? Okay, that's all we need. So by using this equation, we should be able to get this one. All right. Then substitute it to the equation here, right? Equation here and here, right? So we have an equation for the b, and keep it in mind that we got this b by minimizing the wetted perimeter with respect to y, right? So that substitute it to the hydraulic radius, and I am sure you can derive it. This hydraulic radius we can write y is y divided by 2, half of the hydraulic depth. All right. So that is by minimizing the wetted perimeter. Now, what we need to understand is what is this angle? What is this slope? 1 to m, what it should be, right? Or what is this angle if we want to minimize this wetted perimeter, right? Now what I will do, I will write the same equation now in terms of the m. In terms of the m. Why it is? First, there are two variables, y and m. There are two variables. By taking the derivatives with respect to y, we minimize the wetted perimeter, but still we have m. So now what I do, I take the first derivative again, dp over dm, right? Considering m as a variable. Again, make it equal to 0 for minimum wetted perimeter. By doing so, you will get an equation, or the answer, m is equal to like this. M is equal to square root of 3 over 3. In other words, m is equal to 1 over square root of 3. Right. So if you consider this trapezoidal cross section, this is the angle theta, right? This angle theta. Right. This is m. This is equal to 1. So what is tan theta now? Tan theta is equal to 1 over m, right? So the m is equal to 1 over square root of 3. In other words, tan theta is equal to square root of 3. What it is? Theta is equal to 60 degree. Theta is equal to 60 degree. In other words, what it is? it is a half hexagon, right? Half hexagon. When the angle theta is equal to 60, what it means is that this is a half hexagon. Now we have the geometry of the cross section we need. To carry this flow rate, we need to keep A constant, right? And if you use a half hexagon with the angle theta is equal to 60 degree here, then it will minimize this wetted perimeter. All other time, the wetted perimeter will be larger. Minimum wetted perimeter comes when angle is equal to 60 degree, right? And it will satisfy our Q and the area, right? Okay, hope it is clear. So what we did, we separate the variables. What are the variables? We have the Y and M, right? Then we took the derivatives with respect to one by one. Then we minimize it. Then we can get the answer, right? That is the basic idea. So I need you to go through this derivation. I don't have much time to explain step by step. All right, so please go through it. Then what I discuss is for a trapezoidal section. I need you to practice the same for a rectangle. It is much easier. Trapezoidal is complicated one. For the rectangle, it is much easier, and I hope you to get these answers. And you need to prove that the best rectangle section is a half square. Half square. So prove it. Again, for a triangle, it should be a half square, right? So it should be like this. Half square, the best one. So I need you to prove them, right? So please try it. The concept is you minimize the wetted perimeter. Do you have any questions so far? You are very silent, but I am going to assume that you understand it, right? Okay. Right. Now the energy principle. As I said, there are three governing equations. Energy equation, momentum equation, and again, using the momentum equation, we derive the Cauchy-Manin equation. So these are the basic equations we use in open channel design. All right. So now, as I told you earlier, in open channel flow or in pipe flow, there are three head terms we consider: the pressure head, velocity head, and the elevation head, right? So now in open channel flow, this is the velocity head, this is the elevation of the channel bed, and this is the water, the depth to the water surface, right? So that is the total head. Now we define a term called the specific energy, which is with respect to the channel bottom. So we consider the channel bottom as the datum, right? We have, let's say this is the longitudinal section of the channel, and this is the water surface. Now we consider this channel bed is our datum. So the specific energy is defined as the velocity head plus the water level. What is this water level? It is this one. You calculate the velocity head and add to the water depth. That is known as the specific energy, right? So now this specific energy, in this equation, the velocity, we know that we can write it in terms of the flow rate and the area. What it is? Q is equal to AV. So instead of V squared, now I substitute Q squared over A squared. That is the velocity head. Now you understand, for a given discharge Q, this specific energy at any section is now a function of the depth. Function of the depth alone, right? Function of the depth alone. Okay, so why this is needed? Now, if you plot this relation between the specific energy, that is E, and the Y, E and Y, these are the terms we have, E and Y, for a given flow rate. For a given flow rate, what you get is something like this. This is the curve, this one. And there are very important characteristics of this curve that we need to understand. What are they? First is that there is a minimum point here. What is it? The specific energy is minimum here. It is minimum. All the other time, specific energy is higher. When it comes here, the specific energy is minimum. And this is called the critical depth. Critical depth. Right? It is called the critical depth. The depth of the flow when the energy is minimum, that is called the critical flow. All right. Then, right. Then for a given flow rate, you can understand that we have two depths, that is y1 and y2. So you understand, we are talking about the same flow rate, but we can have two depths, y1 and y2. This is the flow rate. For a given flow rate and for a same specific energy, we can have two flow rates. So this y2 is larger than y1. So can someone tell me about the velocity? What will happen the velocity here? Can someone tell me what will happen the velocity here? Which one is larger? Anyone?
At the point y1, the velocity will be larger.
Exactly.
Y2.
Yes, exactly. When the y1, at y1, that we are talking about a smaller depth. So the velocity will be larger. V1 is larger than V2. This is a very critical point. Why it is? When the velocity is larger, the channel is susceptible to the erosion. That is why, no matter whether it is a concrete channel or a natural channel, we need to maintain velocity in a desirable level. Otherwise, the channel will be susceptible to the erosion, right? So now what will happen? Whenever this velocity, actually the water depth, it is smaller than this critical depth, that is y1 in this case, we call it is, supercritical flow. This is called the supercritical flow. Supercritical. So you understand the meaning of the word supercritical. So we are talking about a higher velocity, right? But when the flow rate is the same, but we have different depth, in this case, if the depth is larger than the critical depth, y2, we call it is the subcritical flow, right? In between, this is the subcritical flow, this is the supercritical flow, and we call this is the critical flow. At the critical flow, the specific energy is minimum, right? Okay. So why this is important? You remember we discussed about the laminar and the turbulent flow. So the parameter we use is the Reynolds number. Now, similar to that, we define another parameter for the open channel. It is called the Froude number. Right? So this Froude number, when it is equal to 1, we call it is the critical flow. If it is less than 1, we call it is the subcritical flow. And larger than 1, it is called the supercritical flow. Right? So that we prefer to be in the subcritical flow condition. Why it is? There we have a very calm water flow, but when the flow becomes supercritical, what will happen? The velocity increases so that the channel is susceptible to the erosion, right? So how do we derive this equation? I will go through it very quickly. Now what we do, we take the first derivative with respect to y, dE over dy. Now the Q is constant. Q is constant. But A, is it constant? No. A change with the y. Right? So that is why we consider here dA over dy. Right? So take the first derivative, you end up with having this equation. Now what is this dA over dy? You remember the small areas that we consider, right? dA over dy. Consider a small area. This is dA and this is dy. So that dA over dy is now actually equal to this top width, right? In other words, the top width multiplied by dy is equal to dA. So dA over dy is equal to the top width, right? So how did we define it? Top width, that is this one, right? So top width. So you substitute it here. D over dy you consider as the top width. Now, then area divided by the top width we define as the hydraulic depth. You remember we discussed these parameters. Hydraulic depth, area divided by the top width. So now what you do? You take this one. You take this T here. Area divided by the top width is equal to D. You substitute it in here. Right? So you come up with an equation. Now Q squared over A squared is equal to V squared. Right? So you have an equation 1 minus V squared over GD. G is the acceleration of gravity. D is the hydraulic depth. V is the average velocity. And this is equal to 0. dE over dy is equal to 0 if you are talking about the critical flow. Right? So now V squared over GD is equal to 1. It comes V squared over GD here is equal to 1 for the critical flow. Or what you can do, you can take the square root of this one. The same thing, square root of 1 is equal to 1, right? So V over square root of GD is equal to 1. That is what we define as the Froude number. Froude number. So V divided by square root of GD. And remember, this D is what? It is the hydraulic depth, right? Hydraulic depth. And G is the acceleration of gravity. For the critical flow, this Froude number is equal to 1. All right. Whenever the flow is becoming subcritical, this Froude number is less than 1. Whenever it is more than 1, it is become the supercritical. Right? So that is how we define whether the flow is critical, subcritical, or supercritical. It is similar to the way we define the laminar or the turbulent flow. All right. So I hope it is clear. Do you have any questions? No questions? Okay. So in that case, let me move on. Right? So now, what we do after that, we simplify it for a rectangular cross section, right? Rectangular cross section. So the same equation, you can write it. Now if you consider this kind of a rectangular cross section, this hydraulic depth D is equal to Y, right? Only for the rectangular cross section. So instead of D that you have in here, you can substitute Y, right? It becomes Y. So that the critical depth YC, now you can write in terms of the flow rate and the width of this channel. This is the width of the channel, that is B, right? So it become like this. Now we define another parameter, it is called the Q. Simple Q is equal to the flow rate divided by the width. What is the definition of this one? That is the flow rate per unit width of the channel. Flow rate per unit width of the channel, right? So that is Q. So for the rectangular channel, rectangular channel, you can write the critical depth in terms of the flow rate per unit width and the acceleration of gravity, right? So remember, this is the general equation that we develop for any cross section. But what we simplify here is the equation for a rectangular cross section. This is just an application of this equation. All right. Right. Do you have any question? I'll give you like 2 minutes. And if you have any questions, please ask. Students, do you have any questions? Kasun, is it clear or not? So far, is it clear?
Yes, clear.
Yeah, actually, we are going a bit faster now. I understand it. But I noticed that the booklet provided to you is very detailed. So when you listen to this presentation and when you read that booklet, I'm sure you can manage it. All right. It is a good booklet, actually very detailed one. All right. Okay. So let's continue then. Right. Now, similar to the previous case, what we need to understand is what will be the critical depth. And then if we find out this critical depth, whenever the flow depth is less than the critical depth, we understand that it becomes supercritical, right? So understanding this critical depth is important. And we can calculate the Froude number as well then. Now, similar to the previous case, the researchers have developed a type curve like this for calculating this critical depth. So there, what you need to do, you substitute the flow rate here. Then you need the B, acceleration of gravity, and then you need the slope of this. If it is a trapezoidal channel like this, then you need what is this M. By knowing these parameters, you can find out this ratio here. What it is? M YC over B. So by known values here, you can find out what is this parameter. By knowing M and B, then you can find out YC, critical depth. In your assignment, I have included one question, right? Either you can use this one or you can use the equations itself to find out this critical depth. Okay, so please try the assignment question. You will understand this. Now, if we are using a circular cross section, then it is like this. We have the diameter, that is D naught, and this is the critical depth YC, right? So there again, you need the flow rate, acceleration of gravity, diameter. By knowing it, you can find out the ratio YC over D naught, and then by knowing the D naught, you can find out the YC, right? So that is the advantage of this kind of type curves, right? In your assignment, I have included this example. Actually, for the lecture note, it is an example, but in your assignment, it is a question. I will explain the idea behind this one very quickly, right? So what it say, this is an hydraulic transition. You know that, especially in irrigation schemes, we have very mild slope like this. But in some case, we cannot avoid this kind of steep transitions. Again, we can maintain a mild slope like this. So this transition must be properly designed, right? So that this question is the case like this. So the flow rate for this one is given 15 meter cube per second. I need you to understand the magnitude of these numbers. 15 meter cube per second. It is a quite high flow rate. And at the entrance, the depth is 3.6 meter. Then you can calculate what is the total head here. Total head. You have the elevation difference, you have the y, and by knowing the y and the width of the channel, you can also find out what is V1. So the total head is V1 squared over 2g plus y1 plus this elevation difference. That you can find it out. After that, it says that when the water comes to this section, here the total head loss is equal to 0.1. Then it asks you to find out these y1, y2, y3, like that. What is the water depth in this transition? Right? It is that simple. So use the energy equation. Use the energy equation. Every time consider the head loss. In fact, what you can do, you can consider this EGL. Write the equation for the EGL. Every time when you have the equation in terms of the flow rate, in terms of the velocity, substitute it with y. Right? Y is this depth. So that you can find out y. That is the basic idea. So you will use the energy equation here. Is it clear? Please try it. So I'm sure you can handle it. Right. Now again come to a very important part that is called the hydraulic jump. As I said, there is a rapidly varying flow and the gradually varying flow. Now we are talking about the rapidly varying flow part. This one, hydraulic jump. Let me show you a nice video you to understand exactly what this hydraulic jump is. I have limited time, but still I would like you to see it. Can you see this video? Yes or no?
Yes, sir.
Yeah, right. So please see it. Right. Here you can see this region is the supercritical part, right? Supercritical flow. Then here, when somewhere here, it happens the hydraulic jump. The reason is that the flow always try to minimize its energy, right? It cannot maintain this supercritical condition. So it jump, and during this time, the flow velocity, it start changing rapidly. So the flow become turbulent and it reduce the energy, head loss. After that, when the water flows again, that means the flow has become normal condition. In other words, it has become the subcritical flow, right? So we need to understand this phenomenon very clearly, especially in a hydraulic design. What it is, why it is. The reason is that we are talking about a turbulent flow condition here, right? So we need to understand it and properly design it, right? So I will show you what happened in the actual case. You see this one. Right. Hope you understand it. I have given you the link. So please watch it. All right. So that is the hydraulic jump. Now, again, we use the momentum equation to design or to find out a governing equation for this. What are the forces we have? We have the pressure force coming from both sides. That pressure force, we know that the pressure is equal to the gamma H, gamma multiplied by the depth y, right? Then that is the pressure. To find out the pressure force, what you should do? You should multiply it by the area. Now I am considering section with unit width. I will consider this is 1 meter unit width. And this is y1, right? So A is equal to this one is equal to 1 meter multiplied by the y1. That is the unit width. All right. So the F is now equal to the pressure multiplied by the area. So you have this equation. Same F2, you can write it like this, right? So now F1 minus F2, you can write in terms of the specific weight and y1 and y2. That is equal to, if you assume the time rate of accumulating the momentum inside this control volume is 0, then you can write momentum flux in minus, sorry, momentum flux out minus momentum flux in, right? That is momentum, you know that you can write m dot, that you can write rho AV, right? So the rho is the density, right? AV is the flow rate. Now we are talking about the unit width, so that the Q become simple Q. Q for a unit width is the simple Q, right? So that is why you see the simple Q here. AV is equal to Q. Since we are talking about the unit width, we can write it simple Q. So the rho Q V2 minus V1, right? Now V1, again, we know that Q is equal to AV. If you are talking about a unit width, this is Q is equal to the A times Y, right? A times, sorry, yeah, the velocity times Y. Yeah, so that we can write this one now. This V1 is equal to the Q divided by Y1. Q divided by Y1. And V2 you can write this is the same flow rate Q divided by Y2. So substitute them in here, right? So F1 and F2 are in terms of the specific weight and Y1 and Y2. Then we have V2 minus V1 coming in terms of the Q and Y1 and Y2. So substitute it here, you have this equation, right? So now we know that this one, that is the Froude number. It is in terms of the velocity and the depth, right? So Froude number, if you calculate at the entrance of this one, NF1, then you can substitute it like this. So bring this Froude number into this equation for the Y1, right? Then you end up with having this equation. See this equation now, what you have there. What you need to find out is what is the depth that it changed, how it changed. That is in terms of the entrance depth, Y1, that is your supercritical flow depth, Y1. Then you have the Froude number. Then you have you can calculate the Y2. A very simple equation. Y2, it is in terms of the Y1 and the Froude number. Substitute them, you can find out Y2, right? In a design, this is very important us to understand. We cannot expect the channel to behave like this, right? So we have to expect this kind of a hydraulic jump. Then we have to expect this Y2. So this is the depth that you should design. Otherwise, if you design only for Y1, then when the hydraulic jump happen, the flow rate increase and become the subcritical, so that the water will start overflowing the channel. So you need to understand what is this Y2 to avoid the water going out from the channel, right? So that is Y2. Okay, again in your assignment, there is a question, I think this question. Yeah, So basically what it says is that there is a 10 feet wide rectangular channel. This rectangular channel, the width is 10 feet. Be careful, we are talking about the US unit system, so that the acceleration of gravity, I think 32.2, okay, feet square, right? S square, sorry, feet S square, right? So you have the width 10 and the flow rate Q is equal to 500 cubic feet per second. At a 2 feet depth, before entering the jump, compute the downstream water depth and the critical depth. Find out what is the critical depth. Check whether this flow 2 feet is supercritical, subcritical, or the critical. Hopefully, I'm sure it is going to be supercritical flow. Then this supercritical flow when become the go through the hydraulic jump and become the subcritical. What is this Y2? Find it out. So that is the question. Okay, I hope you can manage it. Right, now, what is the energy loss in this hydraulic jump? As I said, when the flow becomes turbulent, energy start losing, right? So what is the energy loss? That is delta E. Basically, what is the total energy or the specific energy in this case we had before the jump and the specific head we have after the jump? That is the head loss, right? So substitute this equation again, you will get it in terms of Y1, Y2, right? That is the good thing. So by knowing Y1 and Y2, we can calculate what is the energy loss for this hydraulic jump. Okay, so please go through this derivation, a simple one, then you can get this equation. So now you understand when we have a rapidly varying flow, we can find out what is Y1. Sorry, by knowing Y1, we can find out what is Y2. That is, if you know what is the supercritical flow, we can find out what is the subcritical flow. We also can find out what is the energy loss. Right? So these are the most important two parameters in a design. Right. Do you have any questions? Right. If there is no question, actually, this is what we discuss now. That is rapidly varied flow. So we need to understand once the hydraulic jump happen, what is this depth, right? So this question or this part here is now about the gradually varied flow. That is this one. Now, if you have a sluice gate like this, and if you open the gate very slowly in irrigation schemes, where this is very common phenomenon. If you open the gate, what will happen? There is a larger water body behind it, so that the water start coming out, and most of the time it is supercritical flow. So then the flow start gradually varying like this. At one point, it start the hydraulic jump, right? So now what we are discussing is this part here, gradually varied flow. All right. So to discuss it, again, we consider the total or the energy concept, total energy, how this energy change. All right. So the total energy head at any section in an open channel, we know that we can write it in terms of the velocity head, water depth, and the elevation head, right? So now this V, we know that Q is equal to AV, right? So that the V we can write in terms of the Q and the cross-section area, this one, right? Now what we do? To compute the water surface profile, what we interest? We need to find out this water surface profile, how it change. So we must first obtain the variation of the total energy head along the channel. How the total head, that is H, change along the channel, that is X direction. X direction, how the total head change. What we do? Simply take the derivative dH over dx. Take the derivative gh over dx. Now again, Q is constant, but A is a variable. Right? A is a variable. Why? The A change with the X. You can understand. A change with the X. Right? So dA over dx. Now then dy by dx. Y also change with the X. The depth change with the X. So the dy by dx plus dz over dx. What is this dz over dx? Can someone tell me? dz over dx. Anyone? What is the meaning? dz over dx. You can put the answer on the chat box, or you can speak. Elevation change with the x. What it is? That is the slope. Yes, exactly. That is the slope, right? So now you see what we need to understand is this one, dy by dx. How this y, right? When the flow gradually vary like this with respect to the channel bed, how this y change, right? So the dy by dx is our interest. That you can find it out in terms of knowing how the energy grade line change with the x, dH over dx. That is the energy grade line. How it change with the x, dz over dx is the slope. And by knowing the flow rate, by knowing the top width and the cross section area, you can find it out, right? You can find it out. Okay, so let's see now what we do. We first need to understand how this energy grade line change with the x. Energy grade line, if you draw it, it has a negative gradient like this. We know it. Why it is? We have a negative gradient because of the head loss. So earlier we defined the slope of the energy grade line, and we say that it is equal to SE. SE is the slope of the EGL slope, right? So that is equal to dH over dx, and we have a negative sign here because it is decreasing because of the head loss. Now what we do? We jump to the, yes, we have a chat. This is should we remember this? Most of the equation I can say will be provided, but simple derivation like the area, wetted perimeter, these you should be able to derive. These are very simple things. Other than that, equations like this, equation like this one, right, will be provided. Yes. Okay. Right. Now, yeah, okay, you're welcome. Right. So that what we do, we take the slope of the EGL from the Manin equation. This is the Manin equation, right? So we can get the slope of the EGL from the Manin equation. So we have that one coming from the Manin equation. That is okay. A is equal to by if you are talking about a rectangular channel section. And here we make a very simple assumption. What it is? We are talking about a wide rectangular channel. Wide rectangular channel. What it is? We have a channel like this, but it is a very wide one. So now this B compared to Y, this is Y, right? So B is much larger than Y. So that now you can write this one. y is approximately equal to 0. Here, b plus 2y approximately equal to b. Right? So substitute here, you will end up with hydraulic radius is equal to y. Right? So now you can substitute them into the equation, right? Into the equation, and then you have this dy by dx. That is all what you need, right? Dy by dx. That is how the hydraulic, this y change along the x direction. That comes in terms of this S naught, that is the slope of the channel bed. It comes with the Q, it comes with the B and the A. By knowing them, you can calculate how this dy by dx change. Now, what we derived here is for a rectangular channel. All right. But if it is for any other non-rectangular channels, it comes with two parameters. They are n and m, right? So these n and m must be defined for the non-rectangular channels. Okay. So that is the gradually varied flow. So we discussed about the rapidly varied flow and the gradually varied flow. We also discussed the uniform flow. You remember we developed the Manin equation for the uniform flow. After that, we discussed the hydraulic jump, that is for the rapidly varying flow. Then this equation we discussed for the gradually varied flow. All right. So in your handout, in your booklet, there are examples for all these questions. And the assignment also cover these topics. Right. So I need you to go through the booklet first, then do the examples that you have there, then start the assignment. Okay. That is the way I have planned it. Okay. So I have about 15 minutes. What I thought is, instead of going detail in further, I will do one small example. All right. That is from the Manin equation. The reason is I explained the hydraulic jump, but I did not explain the hydraulic jump and the energy equation, but I did not explain the Manin equation. Right. So this first question in your assignment, please read it, then I will explain it. Please take like 2 minutes to read this example, then I will explain the idea behind it. Right. Let me explain it. Then I will give you about 5 minutes to work on this example. Okay. Then I will explain the solution. Right. What it say? There is a 3-meter wide rectangular irrigation channel. The width of this rectangular irrigation channel is 3 meter here. 3 meter. It carries the flow rate Q, it is equal to 25.3 meter cube per second. A very large one, right? Very large flow rate, right? Then the uniform depth is 1.2. It says that this depth here is 1.2 meter. Determine the slope of the channel if the Manin coefficient n is equal to 0.022. Can someone tell me what kind of channel it is by using the Manin coefficient? Can you tell me about the friction of this channel. Of course, it is given as a irrigation canal, right? Irrigation canal. So you can understand it is kind of a man-made canal, but still it is not a very smooth one. If you go to the Manin coefficients, you will see that the natural canal also start with 0.025 and going up to like 0.035, right? So you can understand that this is the roughness coefficient is higher, so that you can expect a reasonably high amount of head loss in this channel, right? By considering them, use the Manin equation to find out the slope. That is the first thing. Then what it say, if this discharge in the channel is increased to 40 meter cube per second. Now you are increasing it to 40 meter cube per second. What is the normal depth of the flow? Okay, so I will give you couple of minutes. Can you start working on it? And can you tell me what is the answer for the first part? Okay, so I will give you 3 minutes. Right, very good one. We have the answer 0.041. How about the others? Do we have the same answer? Right, because of the limited time we have, let me explain the idea behind it. Yeah, let me see. Right, basically the equation Q is equal to AV. We use the Manin equation. By substituting the Manin equation, we can write this Q is equal to 1 over N area, hydraulic radius, 2 over 3, right? Hydraulic radius, am I right? Yeah, hydraulic radius, then the square root of the slope of the EGL. Now, very important, right? In the exam, what you need to see is that you understand the basics. You remember this Manin equation was developed, and in the original Manin equation, we have the energy slope of the energy grade line, that is SE. But Manin equation was developed considering the uniform flow. So you need to write this one, uniform flow. Then for the uniform flow, SE is equal to S naught. I need to see that you understand this one. Slope of the energy grade line is equal to the slope of the bed, right? So then only you can use S naught here, right? So that is the main point I wanted to explain, right? Now I think the Q is given. Q is what? 25.3 meter cube per second. Be careful about the unit. We have 1 here only if you are using the SI unit. So 1 over 0.0. What is the Manin coefficient? 0.022, right? Then area. It says that 3 meter multiplied by 1.2 meter. 2 meter. Then the hydraulic radius, RH, that is equal to the area 3 multiplied by 1.2 divided by wetted perimeter. What is the wetted perimeter? That is B plus 2 times of Y, right? B plus 2 times of Y. So the B is 3 meter. 3 plus 2 times of 1.2, right? So you can find out the wetted perimeter. Then you know all the parameters except this one, right? So that you can find out S naught. That is easy. But this is the understanding about the question. All right. Now I will explain the second part. What it say now is that the same channel, they increase the flow rate to 40 meter cube per second. 40 meter cube per second. Now they ask you what is the H. This B is given 3 meter. This is 3 meter. S naught you just calculated. Now you have it. They ask you what is this Y, right? Meter cube per 40 meter cube per second. Now 1 over N is still 0.022. RH, what is RH now? 3 plus 2, sorry, 3 multiplied by Y, that is the area, divide by 3 plus 2 times of Y. That is hydraulic radius 2 over 3. Then you also need to multiply this by the area. What is the area? B times Y, right? Then multiplied by the S naught square root of that. Right? Now you see, this is not a linear equation. B, you know it is 3, but the Y is an unknown. So you will have to use your calculator, or you will have to use the trial and error method to find out Y. All right, so find out Y. I hope it is clear. Do you have any questions? Right, we have reached almost to the end of the class. We have about 2 minutes more. Please tell me, I need to get some feedback about the lecture. Do you need any clarification, or do you need any improvement? The point is that next class, maybe me or someone else will do the sediment transport part. Then I will do the groundwater part. For the groundwater, I will spend 2 days. But for the sediment, I myself or Dr. Kasun will do it. So we will do it within 1 class. So we need to understand whether the lectures are going quite fast or do you think that you can manage it by reading the booklet? I need some feedback. Was it fast? I know that it was fast, but I hope by doing the self-study, by reading the booklet, you can manage it. Right. I will stop now. Okay. So you have my email address. Right. This is my email address in the university. All right. So if you have any question, you can contact me. Okay. So I can help you to understand it. Right. I think that's all. Thank you very much for staying with me for 2 hours. Then I will see you next time. Okay. Thank you. Yeah. Thank you very much.